Hi guys. So in this video, we're going to briefly look at the applications of the law of sine and cosine to specific problems in each context. And just as a warm up to kind of remind you what the purpose of these formulas are, I want you to take a look at this question, which is to find the missing side of this right triangle. So go ahead, pause this video, see if you could work out what that missing side is, and we'll come back and confirm your answer. Okay, so what I'm going to do, just so we can refer to this side by name, is I'm going to give it a letter, and I'm actually just going to call it B. There we go, B. Now, hopefully when you're looking at this, you notice it's a right triangle, and if you have 2 out of the 3 sides of a right triangle, we're typically going to use the Pythagorean theorem. If you did think of that and you did it, you'll find that B is actually the square root of 161. The Pythagorean theorem, if you remember, is a squared plus b squared equals c squared, where c squared is the hypotenuse, and a and b could be any of the legs. So I could have just easily called this a, it doesn't make a difference. But once I've chosen a letter for this side, I'm actually going to use this formula. I'm going to rearrange it in a more convenient form so that I have it solved for b. So I can go ahead and just plug in c and a, square them, and simplify it out. So that's where it comes from. So the Pythagorean theorem is super useful when I have right triangles. So what I'm going to pose right now is what happens if we want to find a missing side and we don't have a right triangle. Well, first we need to be able to describe the components of this triangle easily. And since we don't have a specific right angle, a hypotenuse to refer to, we're going to have to get a little creative. So just as a notation element, whatever a vertex is named, we identify vertices with capital letters. The side opposite that vertex, I'm going to identify with the corresponding lowercase letter. So this is vertex A, the side opposite that is side A. For vertex B, the side opposite that would be side B, which in this case is 19. And for vertex C, the side opposite that is 25.3. Okay, it's going to be hard to tell the C's apart, but we'll deal with it. Okay, so now because this is not a right triangle, I can't actually use Pythagorean theorem, but don't you worry because we have ourselves a couple of alternate formulas. So for the first one is actually called the law of cosines, and essentially the law of cosines is the generalized Pythagorean theorem. In fact, if you look at the first beginning of it, you'll notice you see the Pythagorean theorem there, and we'll actually circle back to how we get the Pythagorean theorem out of this generalized law of cosines. But the law of cosines is more powerful because it works on all triangles, not just right triangles. But there is one key thing that you will have to keep in mind. Since there's no hypotenuse, actually the side that you isolate doesn't have to be a special side. You could isolate any side you want to solve for it. So here, if I'm solving for side C, the only thing that is special is whatever side you have isolated in this formula, I need cosine of the angle opposite that side here. So this is always cosine of the angle opposite the isolated side. Okay, so what do I mean by that? Well, in this problem, I'm looking for side A, not for side C. So I could use this same format of formula, but just the letters are being slightly different positions. Since I want to solve for A, I'm going to isolate A. What that means is that the remaining sides are going to be a combination of B and C, and I'll have cosine of the angle opposite that isolated side. So I wind up with a squared equals c squared plus b squared minus 2bc cosine a. And that works for all 3 sides. So whichever side you're solving for, isolate that side, but just make sure you're using cosine of the angle opposite that side in your formula. From here, it's really similar. I'm going to kind of plug and chug. So I'm going to plug in all the corresponding values. I know what B is, I know what C is, and I know what angle A is. It's 95 degrees. So I'm going to plug in all of those values into this formula. And then I'm just going to come over here to my calculator and I'm going to type these values in. So I have 25.3 and I'm squaring that, to which I'm adding 19 and squaring that. And I am subtracting 2 times 25.3 times 19 times cosine of the angle opposite, 95. Now, that's 95 degrees, so I'm just going to take a quick second to double check the mode of my calculator. And I am in degree mode, which means that my calculator will interpret that 95 as 95 degrees, not 95 radians. And that'll give me 1084.9. So that's the a squared. And if I want the a, I could just do the square root of this value. I'm going to highlight that value, hit enter to pull it down, and hit enter again. It is crucially important that you refer back to the actual number value. So I'm importing that number by highlighting and pulling it down. I'm not just writing 1084 and taking that square root. That creates what we call compounding errors, which is my approximation from the middle of the problem is going to throw off my final answer at the end. So you want to make sure that you're only rounding your final answers. But that brings me to that. So I get 32.9 is the length of that missing side. So it's not too bad. It's just a little bit more complicated of a calculation than the basic Pythagorean theorem. Okay. It's actually really interesting, as a quick aside, that you get the Pythagorean theorem from this if you have a right triangle. So say I have a right triangle with a right angle A, B, and C. If I look at this law of cosines, I wind up with c squared equals a squared plus b squared, and then minus 2ab cosine c. But when c is 90 degrees, if you remember, cosine of 90 is actually 0, which you can confirm by looking at a calculator. So what winds up happening is that this whole term becomes 0 if c is a right angle, which is how we get the Pythagorean theorem out of the law of cosines. So the Pythagorean theorem is really just a special application. Okay, so how else can we use this law of cosines? Well, we could use it to find angles as well, since it has a formula in it. So here my directions are to solve the triangle. And if I'm trying to solve a triangle, I want to find all angles and sides. So I want all angles and sides here. Now, I already have all three sides, so skiddly-doo, that's convenient for me. And I'm going to use the law of cosines to find side, or rather angle C first. Okay, so this would be angle C. Now, rather than using this form of the formula, I'm actually going to solve for angle C, so I can isolate it so that I can just plug the numbers in and I don't have to work with any complicated number expressions. So I'm going to do that first by subtracting a squared and b squared over. And subtract that from both sides. So I'll get, and I'm going to write it this way for a reason, negative a squared minus b squared plus c squared would equal negative 2ab cosine of angle C. And then I will go ahead and divide both sides by negative 2ab so that I can isolate cosine of C, which when I divide these values, the negative here will cancel with this negative, and this will now be minus. So I wind up with a squared plus b squared minus c squared all over 2ab. And that's where I'm going to leave it for when I plug in my values. So then I'm going to plug in each of my values, and I'm going to help by identifying them. So if this is angle A, then side A would be opposite that. This is angle C, then side C would be opposite that. And if this is B, then that leaves side B for here. That tells me cosine of C should equal a squared, so that would be 16 squared plus b squared is 15 squared minus c squared is 26 squared all over 2 times 16 times 15. Okay, I'm going to figure out what that approximately is. So I'm going to go over here and I'm going to type in 16, oops, put it on my calculator. So I'm going to type in 16 squared plus 15 squared minus 26 squared. Hit enter. I'm going to divide that by, I'm going to put parentheses because I'm dividing it by 2, the product of 2 times 16 times 15. And I want to get that product before the division, hence the need for the parentheses. I'll hit enter. It gives me that ratio. Okay. Now, if I'm looking at my diagram, I can see that angle C is an obtuse angle. So that means that if I'm thinking about the unit circle, I'd expect it to be in quadrant 2, hence the negative. on my ratio here. And in fact, for cosine, I can actually just get that quadrant 2 angle immediately by applying the inverse. So if I apply the inverse to both sides of the expression that I now have, so I have cosine C is equal to negative 0.4 essentially. If I do cosine inverse of that, I should get C. It would be cosine inverse of 0.4, which will equal, now I'm not going to use 0.4, I am actually going to use the entire, sorry, it's a negative 0.4, cosine inverse of negative 0.4. I will actually go back up and highlight the full number so that I'm not going to get an approximation error. It'll give me 113.96, so if I'm rounding that to the nearest tenth, that's going to give me 113, well, 114 if I round to the negative tenth, the nearest tenth, 114 degrees. Okay. So a couple of things we did is that I solved in general to get a formula so that I can figure out, I manipulated the formula essentially so that I could isolate the angle that I was trying to solve for, and then I plugged in my values and solved for that angle. Now if I'm solving for the triangle, I'm going to repeat this process for each side. It's just going to be slightly different arrangements. So if I want A, I'm going to plug A here, C and B here, and then cosine of A here. Same thing for B. So here are the other two sides, the other arrangements of this formula. If I'm solving for A, then I have angle A in that cosine. If I'm solving for B, then I have angle B in that cosine. I did the same thing for each of these. I isolated the angles, and when I solve for them, I get 34.2 and 31.8. And if we check 34.2, 31.8, and 114, they do add up to 180. So that tells me that I have viable angles for inside of a triangle. Okay, so the law of cosines is helpful for solving for sides and angles. And in situations where the law of cosines doesn't work, we also have the law of sines. You can see lots of videos for the proofs of both laws, but the law of sines basically says that the ratio of any one side divided by sine of its opposite angle is equivalent for all sides in a triangle, okay, as seen here. The way the law of sines works is it's very, very similar here. Say I'm looking for side KP, that's the side joining point K to point P. Another way of labeling that is side H if we're using our lowercase letter approximations. And I can do that by finding any ratio of an angle with its opposing side and setting it equivalent to this one. So in my case, 32 over the sine of its opposite angle, 55 degrees, must be proportional to H divided by the sine of the angle opposite H. And that's essentially what this formula is saying. So if I solve this for H, I get that H is 32. I'm going to multiply both sides of this proportion by sine of 48. So 32 sine of 48 degrees divided by the sine of 55 degrees. So it's just a different formula, but it's the same basic algebra to isolate the terms. And I'm going to go over here to my calculator, and I'll type in 32 sine of 48 degrees, close parentheses, and then divide that by the sine of 55 degrees. Okay, I get 29. So H is going to be approximately 29 units. So it's a similar kind of process, just a different formula. And as a tip for helping you know which formula to use when, if you think back to different combinations you could have, if you have three sides, we can use the law of cosines to find any one angle opposite any one of those sides. If I have a side angle side combination, I could find the side opposite the given angle. And then if I have angle side angle or angle angle side, I can use the law of sines to find missing sides. The only one thing that I'm going to put a button on is what we call the ambiguous case, is if you have an angle side side situation. If you remember back to geometry, that was not a way for proving triangles congruent. It creates a problem, and we'll look at that in a different video. Take care.